Small changes in the initial state can lead to very large changes in the final state. In nature, things change. That is the basis of all our entire nature. Everything fundamentally starts from Newtonian equation of motion. What is non-linearity? What is nonlinear dynamics? Uncertainty principle, Newton's laws, quantum mechanics, non-linear dynamics. Prediction becomes difficult. Prediction becomes sometimes impossible. Change is inevitable.
So, sir, right off the bat, I want to ask you about chaos theory. One, it is a relatively new field, if I'm not wrong, and it's not that common in the circles that we come from, like biologists and people involved in biosciences. So, sir, how is it that you would explain it to us? What is chaos theory, and why is this the domain you've chosen to work on?
Yeah, so the notion of chaos actually forms part of what is known as nonlinear dynamics. I don't know, as students of science, you are all familiar with dynamics. Dynamics essentially corresponds to evolution of physical systems, including living systems. So this dynamics is essentially based on Newton's laws. So all of you, I'm sure, are familiar with Newton's law starting from school days onwards. And in particular, the second law says the rate of change of momentum is directly proportional to the forces acting on the system. So anything and everything in this universe is being acted upon by one or more forces. Take any system, okay, there is always at least one kind of force acting. For example, consider the planet. You have gravitational force.
Multiple forces acting on a system.
Consider the electrical charges. You have electrostatic or electromagnetic force, etc. So the force is fundamental. It's inevitable. When it acts, the Newton's geniusness is that he had identified the correct cause, which makes things change. So in nature, things change. That is the basis of all our entire nature. Change is inevitable. Okay, just like in Bhagavad Gita, Lord Krishna tells, so change is alone unchanged. Everything else change. Change is inevitable. Okay. So the rate of change of momentum is directly proportional to the force acting on it. Momentum is you represent the state of a physical system by position and momentum. Okay. So based on which Newton is considered to be many scientists consider the greatest intellect ever to be born on this earth, because he had identified the basic laws of science, and in addition he also gave the logical mechanism with which you can proceed to analyze the consequences of these laws, namely calculus.
Cause and effect, if I'm not wrong. Dealing with the cause and effect of multiple forces.
Yeah, so the cause is the force and the effect is a change. Change in the momentum, so change in the state. Position and momentum changes. Okay. So cause and effect, consequence is Newton's laws, and Newton went on to give a mechanism through which you can analyze these consequences, namely calculus, as I said, the art of calculating changes. So you can formulate this this relationship through differential equations. So you identify differential equations for once the force is given and the nature of the system is given, whether it's a single particle or many particle system. You say n particle systems. So how changes take place for this system, and that is the evolution of this n particle system. And you have n particle dynamics. So you have to solve this dynamics, and then you talk about classical dynamics, and then quantum dynamics. So in the last century, you know that you also incorporate the additional feature of uncertainty principle over Newtonian formulation. And you have quantum mechanics. And now you talk about quantum computing, quantum technology, quantum materials, and so on. Okay, but everything fundamentally starts from Newtonian equation of motion. And the dynamics follows by the study of the underlying mathematical equation, namely differential equations, as initial value problem. Because this initial value problem means you have a pendulum, you do experiments in your lab, there are hundreds of such labs.
Right.
So there will be pendulums, etc. But how you specialize to the pendulum you have in mind in your lab. you specify the initial conditions. So that means this particular pendulum you identify. Okay. Then you follow, starting from this initial condition, that is initial position, that means in your lab, and the initial momentum or velocity you give to that pendulum, you pull it apart and allow it to oscillate. And then you calculate the period. Okay, Newton's equation of motion tells you what is the period and so on, and how this system will evolve. You have the time trajectory that then you extract from the study of this. So this is how the simple system you identify. But for example, in this room there are 10 power 23 average molecules or atoms flowing around. So why the temperature is now 27 degree in this room? How it comes about? The molecules or the atoms collide, they take away energy and so on. So you calculate the average properties of these atoms, and then average energy. It ultimately turns out to be 27 degree when you calculate in terms of temperature and so on. So you get 27 degrees. So that's how you study the dynamics of the underlying system. The same thing for biological system. You consider the brain. So what does it consist of? It consists of billions of basic entities called neurons. So you're all biology students, so you know the basic entity of the brain is the neuron. So these neurons, then they interact, and you know that each neuron has three basic structures, namely the central soma or nucleus, where the information is processed, but from the nucleus, tree-like dendrite structures emerge, and they collect information from other neurons. Then this information flows through cylindrical structures called axons. So it is only electrical signal propagating. Then you have laws of physics. Based on that laws of physics, then you can form the dynamical equations, Hodgkin-Huxley equations. I think it's a system of 5 partial differential equations, then which you can reduce to ordinary differential equations. And this Hodgkin-Huxley, you know, they got Nobel Prize in the 1960s, I think. I don't remember exactly the year. They got Nobel Prize in physiology for inventing this Hodgkin-Huxley equation for the propagation of electrical signals. And through the study of this equation, you can identify how the electrical signals propagates. And then it ends up in the synapse. So that releases chemicals, and that is absorbed by the other set of dendrites, the other part of the synapse, and it goes to the other axon of the second neuron, and it gets the informations are integrated at the synapse of the next neuron, and so on. So this is how the information propagates. And you simplify this as yes or no, whether the electrical signals propagates or it doesn't. So that's why you say it's binary or and so on, +1 or 0 or +1 or -1, you represent that. And so a simple model of an electron, of a neuron, you represent in terms of perceptron. Okay. An engineering model of neuron. And so you have a large number of neurons. You modify or you represent many of the other physical systems in terms of these neurons. And this is what machine learning and neural networks, the study of these kind of artificial neurons. So you have the biological neuron, and based on which whether electrical signals propagates and go to the other neuron or not, you represent by in terms of these binary numbers, +1 or -1, and how it propagates. This is what I talked about, the half-field neural network yesterday.
Yeah.
Okay, and the physics Nobel Prize was given to this kind of biological related, but engineering or computer science work. Okay, and then Boltzmann machine, where you introduce the so-called Boltzmann distribution of energy. This is basis in statistical mechanics, thermodynamics. So Hinton, then and his co-workers, students, made use of this half-field network to identify this Boltzmann machine as the basic entity, this generative artificial intelligence, as basic model for generative artificial intelligence. So half-field network was invented in 1982, and 3 years later, 1985, Hinton and his students generalized this, identified the Boltzmann machine, and this forms the basis of machine learning and artificial intelligence nowadays, which has been further modified through deep learning, deep neural networks, reservoir computing, and so on. So this is a field that progresses in this particular way.
Sir, what you're speaking about, so neural networks and machine learning, and what you mentioned, neurons taking signals, transmitting through synapses, and then some outcome happening. Newtonian physics. All of this is based on cause and effect, and it, if I'm not wrong, follows a linear dynamic model, right?
The propagation of neuron as an entity is a highly nonlinear system. The underlying Harkin-Huxley equation is a system of highly complicated nonlinear partial differential equations, which you reduce to ordinary differential equations, which is again a system of highly complicated nonlinear ordinary differential equations. So once you have nonlinear differential equation, what is nonlinearity? What is nonlinear dynamics? Linear dynamics, linear differential equations are characterized by what is known as linear superposition principle. You consider a second order linear differential equations.
So what does that mean?
Differential equation you are familiar, I think.
Yes.
You consider second order. Highest derivative is second order, d square y by dx square, or d square y by dt square. dy by dt, the rate of change of the y variable as a function
So
of
basically
t.
the most you can differentiate of a variable, like the most different.
Yeah, so you have dependent variable, you have independent variable. So how this dependent variable varies as a function of the independent variable. So that is the derivative.
Will it vary because of an independent variable?
Now, for example, the position varies as a function of time.
Okay.
Okay, x as a function of time, x of t. Then you ask the question, as a function of time, how this variation looks like. Dx, infinitesimal change, dx by dt. So that is the first derivative. The second derivative is again d by dt of dx by dt.
So comparing the combination of those two variables, for example, what you said, position with respect to time, comparing the whole thing with another variable now.
Yeah, so the slope as a function of time again. So that is the second derivative. So you have a differential equation. I think in high school, all of you have studied differential equations. First order differential equation, second order differential equation. So dy by, say dx by dt plus some constant to x equal to 0. So this is the first order linear differential equation.
Okay.
Okay. Because the degree of the dependent variable x and its derivatives, degree of the second derivative, is 0 or 1. So dx by dt, the degree is 1 for the derivative of the dependent variable, plus some constant into x. So the degree of x is 1 is equal to some constant. So there the constant into x power 0. So the degree is 0. So in this differential equation, the degree is either 0 or 1. So that is there, then the corresponding differential equation is a linear differential equation. Suppose I have a differential equation dx by dt plus x square equal to 0. Here the degree of the first derivative of x is dx by dt is 1, but the degree of x is 2 because x square you have. Okay. So in that case, difficulties arise because if you have a solution x equal to x1, okay, then alpha into x1 is not a solution. You can check. You multiply throughout because of the x square nature, you will have alpha square into x square coming into the problem. So that is not the original differential equation. You can quickly check. Similarly, if you have a second order differential equation, if it is a linear differential equation, then you can show that there will be two linearly independent solutions. If you have a second order differential equation, there will be two linearly independent solutions. If you have a third order differential equation, you will have three linearly independent solutions. Okay. If you have such number of linearly independent solutions and you make linear combination of them, that's called linear superposition, that will be also a solution. Then in that case, you say the linear superposition principle is satisfied. The corresponding differential equation is a linear differential equation. And this differential equation represents the dynamical system. So you have linear dynamics.
So you can predict the outcomes when you're using the linear differential equation?
Yes. The main property associated with the linear differential equation and so linear dynamical system is the original property is by making observation, you specify the position and velocity. Okay. And so the position is x of t, the velocity is dx by dt, or the momentum m into dx by dt. So that is p. P equal to mv or m into dx by dt. So when you make an observation at a particular instant of time, which as a reference time I take t equal to 0. So at t equal to 0, I have the position, make an observation and its momentum. I pull the pendulum apart. So I have the maximum amplitude and release it, and so the velocity is 0. So I know the at t equals 0, x of 0 is amplitude A. Okay. And x dot of 0, that is dx by dt at t equals 0 is 0. So I have the initial state, initial condition, and I allow it to oscillate. So as long as the oscillations are small, you can represent the oscillation of the pendulum in terms of a linear second order differential equation. Then in that case, I can follow the system exactly accurately for any time. Even if I change the initial position slightly, there will be corresponding slight variations in the subsequently. So everything can be specified accurately in future instant of time also.
So so if you know the initial conditions, you can predict the final outcome. Is what linear equations, if I may simplify.
So even if you change the initial conditions slightly, still the system follows after final time
dynamic.
With small difference only.
Correct.
So there will be no surprise.
So sir, this is what Newtonian physics, I think, it's the hallmarks of Newtonian physics, right? Because
as the force is linear. When the force is linear, the system dynamics is represented by linear differential equation.
And sir, you work on non-linear dynamics.
Yeah, when the force is non-linear, that means the force is not only directly proportional to the displacement, but unharmonically. It is proportional to x plus x cube or x square. That comes into picture, then the rate of change of momentum is directly proportional to the force. That when you represent in terms of the equation of appropriate mathematical equation, for example, for the pendulum itself, at the next order, d square y by dx square is proportional to y or x plus some constant to x cube or x square. So that equation doesn't follow the linear superposition principle because of the reason I just said before.
So because of the force being non-linear,
yes,
you cannot really predict the outcome.
No, when the force is non-linear, the underlying dynamical equation becomes a non-linear differential equation, in the simplest case, ordinary differential equation. Okay. Not every non-linear differential equation will show complexity. So some non-linear differential equation may also show very regular property. But typically, with appropriate forcing, with additional, say, external forcing, which depends only on time and damping, etc. present, even in that pendulum. So you have what is known as Duffing equation. That equation shows sensitive dependence on initial conditions. You change the initial conditions slightly, and then if you wait for sufficiently long time, there will be exponential deviation of the trajectories. So because of this, then you will find small changes in the initial state can lead to very large changes in the final state. Prediction becomes difficult. Prediction becomes sometimes impossible.
Can we, if we want to define the theory, we can, I think, say that very small changes, what you said right now, very small changes in the initial conditions can lead to
very large changes in the final state. Final state is not an infinite time. In finite time, it can lead to very large changes. So, that means prediction becomes impossible.
Prediction of the final outcome, we can't predict where it's...
very small change can lead to very large change.
Sir, what are this went very deep into the theoretics of it, and
you can also construct an electronic circuit, for example. So, for example, one of the basic electronic circuit was constructed by one of my former PhD students who is now a professor at Anna University in Chennai. So, it's called Murali Lakshmanan Leon Shua,
yes.
An electrical engineer.
The MSL model that...
Murali MLC circuit. So, that, standard LCR circuit. So, in the CRO, you get an ellipse. Current voltage picture is an ellipse. So, that corresponds to a period t equal to 1 over 2 pi root of LC, 1 over LC or whatever it is. Okay, L and C are the inductor and capacitor of the LCR circuit. But once you connect a nonlinear resistor, we call Chua's diode, it has the piecewise linear characteristic, which is a highly nonlinear nature. To incorporate that, then you will encounter period doubling as you change the external forcing or one of the circuit components. Then you will encounter period doubling. So period will become twice the original period, 4 times, 8 times, 16 times. Then will enter into complex motion, chaotic motion, where even very minute change will lead to very large changes. So sensitive dependence on initial conditions.
Sir, where do we see this in nature?
So in the brain itself, I said the dynamical equation is represented by Hodgkin-Huxley equation.
So what are the what small changes here are we talking about which would make huge final changes in the neural system?
Yeah, I mean, for example, even in day-to-day life, I mean, normally you are all fine, etc. But sometimes even you discuss with your friend and he says something, just one remark that disturbs your mood very much, okay, which normally doesn't happen. Okay. So very small change, just one word by your friend, okay, that disturbs the state of your mind quite a bit, and you get perturbed and so on. So that's the typical nature. Small change in the weather. Normally, Pune weather, etc., everything is fine. But then somewhere something changes suddenly, and because of that, in a very short time, the weather becomes very turbulent. Suddenly, a large amount of rain, etc. Destruction can happen, cyclone can arise, and so on. So then, prediction of weather is a highly complex non-linear phenomenon.
Sir, it always happens. When I was in school, I used to, whenever there was a red alert in Pune, it used to never rain. We used to always miss school because there's a red alert, and it used to never rain on that day. So I used to always feel like the meteorological
prediction becomes highly complex. Okay, so you expect based on certain calculation, meteorologists make some calculation. Based on that, they expect there will be heavy rain and so on. But
and I think when you look at the history of chaos theory, meteorology is one of the meteorologists and the problems that they faced was a reason why this theory was born.
Yeah, originally it was Edward Lorenz. He was a meteorologist, physicist, atmospheric physicist at MIT, I think. So, in the course of his study on weather dynamics, he took up the so-called Navier-Stokes equation. So, Navier-Stokes equation, one of the fundamental equations describing complex situations like weather and so on. And then, by identifying the most critical factors, this Navier-Stokes equation is a complicated system of nonlinear partial differential equation in 3 space and 1 time dimension. So, through a series of arguments, Edward Lorenz reduced that complicated system to just 3 basic quantities corresponding to temperature and then energy difference or something like that. So, for 3 variables, and reduced to a system of 3 coupled first order ordinary differential equations. So, that study of that equation brought out all this extreme sensitiveness to initial conditions. So, and he coined this name because very small change in the initial state leads to very large changes in the final state. So, prediction becomes impossible. He coined this terminology chaos, complexity.
When we talk about chaos in general, I think the general terminology, we just use chaos like that, right? If there's too much noise, if there's so many things happening, we say that it's a chaotic atmosphere, it's chaos. But in physics, this is how small changes in the initial
very small change leads to very large change. So prediction at that point of at that instant is impossible because you make even small changes even on the 4th decimal, 5th decimal. So even within experimental errors, inaccuracy, even such changes can lead to very large changes.
I think when Lorenz was doing it, he was seeing the 3rd decimal, right? Like till the 3rd decimal, he saw that.
Yeah, the parameters in the 3rd decimal. So you change the parameter, then that leads to very large changes. So he was wondering whether he had made anything wrong in his calculations or anything, etc. Then he identified that is the nature of the system. And then if you go back in time, as early as the 19th century, in the beginning, 20th century, beginning of 1900s, Henri Poincaré, one of the greatest mathematical physicists from France, he was studying the 3-body problem. You know, the 2-body problem, the sun and the earth, or the earth and the moon. So the 2-body problem, the main force is the gravitational attraction. So you write down the equation of motion. But then for this sun and the earth, you write down the Newton's equation of motion. Then you can go to a center of mass coordinate system. Then you can remove the relative differences, and then you get a system of 3 coupled second order differential equation for one of the dynamical system. And so that equation you can always solve, the result of which Kepler's, you get Kepler's laws. So under gravitational attraction, you get the Kepler's 3 laws.
So the Kepler's laws are just based on two-body
problem. Then if you separate out the relative coordinate and with the other one, then you essentially reduce the 2-body problem to your 1-body problem, which you can solve. And you get the Kepler's 3 laws. Now the question is, of course, in the planetary system, Sun and its 8 planets are there. Okay, so take Sun, the Earth, another planet, Venus, for example. So treat that the effect of the force of the third planet as small. Okay, perturb this 2-body force with the third action of third planet. So at that point of time, I think the king of Sweden or somebody posed this problem. Ask, can anybody solve this 3-body problem? Okay, and then for who solves the problem, you will give a big award or something. So Henry Poincaré took up this problem. He struggled. Ultimately, he came to the conclusion that small changes in the initial state can lead to very large changes in the final state. So prediction becomes impossible. And the consequence, so this is exactly what Edward Lorenz, almost 60 years later on, had identified. But Henry Poincaré identified this in what we call as a Hamiltonian system, the 3-body problem. It's a conservative system. I don't know if you are familiar with these notions. So in that system, we identified the sensitive dependence and initial condition. But the system studied by Edward Lorenz is called a dissipative system. So that system also shows sensitive dependence on initial conditions. So there is 60 years earlier, again, the notion of chaos has been identified, and Henry Poincaré said that 3-body problem cannot be solved exactly. You can only make approximate analysis. So even now the 3-body problem cannot be solved. So you can obtain very accurate results by using supercomputers and so on. But unlike the Kepler's law for the 2-body problem case inverse square type, if you have the second perturbing particle system is present, that system cannot be completely solved in terms of analytic functions and so on. Okay.
Sir, when I was reading about this particular domain, I also came across this problem called the predator-prey model, which also follows non-linear dynamics.
Yeah, again, we have studied this many generalization of this predator-prey problem. So again, it's the interaction of prey and predator. That interaction term is a non-linear term. Non-linear in the sense linear superposition. Because of this additional interaction, the linear superposition principle fails. And there again, as you change the strength of the controlling, what we call control parameter, that is the strength of the interaction, slowly, then you will have limits like periodic oscillation. And then as you change the strength, then it can get doubled, and then ultimately it may end up in complex.
So in simple terms, how can we explain the predator-prey model, like in a very simple way, since it relates to people who study the environment, ecologists, biologists?
Yeah, at sufficiently low strength of interaction, then you have when the predate, for example, I think the standard example says is there's a large fish and small fish is present, and then the large one can eat the small ones and so on. But there will be equilibrium. So at low interaction between these two, the population, even if it decreases, then it can increase and so on as a function of time. But as the strength increases, then the population increase in the prey can lead to large changes in the predator and vice versa. But as the strength increases, even more complex, when you have additional interaction, even more complex changes can take place, which may become highly unpredictable as the strength of interaction increases. So that is again a consequence of this non-linear interaction between the predator and prey. You incorporate additional interaction also into the problem, then you can have such complex changes in the population density of prey and predator.
So they also coined the term butterfly effect for the similar
Yeah,
phenomenon. That
yeah. This is what I just forgot. So when Edward Lorenz identified that very small changes in his system of three first-order coupled nonlinear differential equation leads to very large changes when his computer told the results, the time series. Then he coined this word butterfly effect. So to represent his results, as small as a change as a consider the weather, evolution of the weather. So in South America, Amazons start from an initial state when there is a butterfly, it doesn't flutter its wings. So you consider how the weather is evolving by solving the associated Navier-Stokes equation. And look at the weather at the state of Texas in North America, in the United States. Now, consider a situation where the butterfly had slightly fluttered its wings. So that means the air in the Amazons is extremely small, given rise to extremely small change.
right.
That change, that extremely minor change, can, in a few days' time, lead to the state of weather in the state of Texas, which is quite different from the state when the butterfly had not fluttered its wings. So cyclone or more complex situations could have arisen in the state of Texas.
So
small
something
change.
as simple as a flutter of a butterfly can lead to a cyclone.
Yeah. So to dramatize the kind of effect of small change can lead to final evolution. Okay. It's not exact. You're not identified such actual butterfly fluttering its wings and leading to.
I think that's pretty complex to even do that.
To dramatize the kind of phenomena he had identified. A smaller butterfly fluttering its wings somewhere in the Amazon leads to a complex state in the evolution of dynamics in the state of Texas. Okay.
So to all the students who are studying physics right now and just in STEM, in science and all other allied fields, why should someone look deeper into this non-linear dynamics and this theory? Why should someone probe into it and study it more?
Yeah, if you want to study, our life is very complex. Okay, every day you encounter in this country, for example. So in the state, Maharashtra, so you look at the newspaper every day, some complexity in the city of Pune or in Mumbai or in the state or you come to Tamil Nadu. So many, the way in which things are evolving is so complex. So life is very complex. So you would like to understand the complex phenomena like the formation of cyclones or more complex weather. So many things are taking place every day in nature. So you would like to understand all of them. As I said, all regular standard phenomena will be described in terms of nonlinear dynamical systems.
So at the end of it, we come to a conclusion, as even the French physicist, he came to the conclusion that the three-body problem cannot be solved. That's where we come.
Yeah, you cannot leave that. You cannot just say that this problem cannot be solved exactly analytically. He didn't say that you cannot get accurate results. So by solving, it cannot be solved means it cannot be solved in terms of analytic functions, like the case of two-body problem. The two-body problem can be reduced to a single-body problem, and then you can completely solve it. And from which you say that every planet moves around the sun in elliptical orbits. Equal areas are swept out in equal times, and so on. All the three laws can be exactly deduced. But when you say the three-body problem cannot be solved, you cannot get such results. But then, by careful analysis, you can get step by step what will be the nature of evolution at the next instant after 10 years or 20 years. You can try to make predictions. But you may go off. You try to predict the weather every day. Most of the time it will be accurate. But as you say, that they give you leave saying that it will be heavy rain or cyclone, but it doesn't happen. So it can happen because there is intrinsic uncertainty present. And that comes by studying such nonlinear evolution equations.
And the philosophy behind studying, I think, also underlies the fact that sometimes we do study things and the outcomes, as you said, sometimes the outcome is not as predictable as linear systems,
Yes.
but then that is the solution.
Yeah, initial conditions, you can solve the problem, you can follow it for all times. Okay, so if you are exactly 100% accurately start with that initial condition, you will follow that time trajectory. But there will be always inaccuracy in specifying the initial conditions, because you have to do experiment. You may have to make observations. There will be always some inaccuracy. So even though the mathematical equation representing that phenomena is considered to be more accurate, but making observations, there will be always some inaccuracy. So analyzing this mathematical equation for two different initial conditions means normally you will expect it has to follow each other. There is a small difference initially, finally also a small difference. But when you have such nonlinear force, nonlinear interaction, it may lead to results which can be quite different from the previous initial conditions. So you should be aware of that. Okay. So for specific initial conditions, yes, solving the equation of motion, you will be able to make the prediction. So normally you expect how the system will evolve for a large future time by solving this differential equation subject to that initial condition. But where inaccuracy will arise is in your observation. So be aware of that. What will be its consequence? That's what you identify by studying this nonlinear interaction. But then there are lots of consequences of that. You talk about synchronization, chaos synchronization, and so on. You can make use of this for practical purpose also. So the notion of chaos can also be extracted in certain useful sense in the form of chaos synchronization and so on. So
the eruption of this theory, chaos theory, that there exist systems which behave in this non-linear sense, where the initial conditions may have these non-linear forces, and then the final outcome can be much more in magnitude. This, I think, comes very opposes the very notion of the deterministic Newtonian physics, if I'm not wrong, like Descartes and Newton and all the everything that was happening in physics in the 1800s, late 1800s.
They have not foreseen perhaps at that point of time that the forces you classify as linear and non-linear forces can not, as I said, not every non-linear force will lead to complexity.
Okay.
Only when certain type of, for a given system, certain type of non-linearity, when they combine together, may lead to such complex behavior. So which non-linearity, which kind of non-linear force will lead to complexity, etc., that's again a complex mathematical problem, okay, which we have to analyze and identify.
And so all of these topics will come from the West, right?
Modern science. I'm not talking of the entire science. Modern science has essentially, I would say, emerged from the study of Isaac Newton and his followers, different parts of Europe and so on. So it has come from West, and we are catching up with. When we are able to learn all these things and come with our own theories, own findings, etc., then we will be able to we will be able to lead the entire world.
We hear talks about Viksit Bharat and being rooted to the culture that we come from, and then also being in touch with these concepts, Western concepts from all around the world, and still being rooted to our culture. So you even mentioned Bhagavad Gita earlier, that change is inevitable.
Yes.
Do you find any, when you're doing your research or the research that you've done in your past, do you find any links between the culture in India or the texts from Indian subcontinent, religion, etc., with the theories that you study? Do you find any correlations between them? Since I think chaos also is something that makes us very, it's not a common thing that you hear. It's something surreal. It's something happening which we can't explain really. So do you find any correlations such as that?
Yeah, our culture, our society, our experience, yes, does play a very important role. I mean, I had interacted with many Western scientists. I had been in different countries all around the world, particularly in the West, including US. and they had visited my group, for long times. They have stayed with us. Yes, they have their own good, what we'll say, kind of properties, and some aspect they're very individualistic and so on. But whereas we tend to be more because we are all family oriented, holistic, and so on. So there is differences in the approaches, but ultimately it's all human beings. There are some basic features which are common for all human beings. So as we interact more and more with people around the world, I think we will learn some of their best practices, and we try to make use of those properties and leave aside which we feel is not important to us. So, but we will make use of our best practices and make use of the knowledge that comes from other people, from outside our culture and so on, so that we can grow up and we can look for this Viksit Bharat by 2047 and so on. Yes.
Sir, why did you go into theoretical physics?
No, each one has his own interest. Somebody likes biology, somebody likes law, humanities, or economics, and so on. So fundamentally, I had some interest in from my young days in mathematics-related topics. Then when I joined BSc Physics and so on, dynamics attracted me very much. So as I entered postgraduate and so on, this quantum mechanics, classical mechanics, dynamical studies, associated mathematical physics attracted me. And during the second MSc, I did my MSc at Madras Christian College in Tambaram in Chennai. On Saturdays, we used to have intercollegiate class at that time. In entire Chennai, at that point of time, only 2 colleges were offering MSc Physics. One was Presidency College, that was on the seashore, Marina Beach. And Madras Christian College, it was the other end of Chennai. We used to go to the University of Madras, where Professor P.M. Matthews was giving common lectures in quantum mechanics to both these college students. That's where I met my future mentor, Professor P.M. Matthews. So at the end of my MSc, I went and asked him whether I could join your group. Then as he said, he invited me. So I did my PhD under his mentorship. He was a very great physicist, but he was theoretical physicist. So I naturally entered this area of theoretical physics, and I pursued my interest in dynamics. So he gave me full freedom. A notion of nonlinear dynamics was just emerging in the 1960s. The notion of, I didn't talk about these solitons, these are localized structures. This notion of solitons was emerging, and it is more of mathematical in nature. So I was very much interested, I got interested first in solitons, what I call as integrable nonlinear dynamical systems. And then that study of that kind of systems naturally led to non-integrable or chaotic systems. So the study of nonlinear dynamics forms both of integrable systems and non-integrable systems or chaotic systems.
So that's where you got into this field.
I think I have enjoyed my research career quite a bit. I continue to enjoy. And coming and visiting MIT Peace University has been very nice experience.
So is this the first podcast that you're doing? Or have you done something like this before?
Online, I think somebody had interviewed me.
Okay.
But this podcast in person, I think this is the first time that interacting with young people like you. So it's very nice that you are all so much interested. So I wish you all the best. So, yeah.
This was very interesting, sir, because it deals with subjects that are not related to our syllabus or something that we have to study, something that we've opted for, something completely different, and it gives us perspective. It gives us perspective into what kind of domains exist and how they also involve and are related to biology and biological systems.
Okay.
So this was a great talk, and I think we're towards the conclusion here. We have a segment.
So if you were never a scientist, if you never stepped your foot in this field, what would have your career be?
I would have been a farmer.
Great choice, sir.
Because my father is a farmer.
Yeah.
So. Yeah.
Wonderful, sir. So what's your favorite lab equipment?
No, I'm a theoretical physicist, so computer.
Okay. but any time you have worked in lab and you feel
Yeah,
this
I
equipment
work
is-
also on electronic circuit. I talked about MLC circuit.
Yes.
Yeah.
And even in theoretical science, which theory fascinates you the most?
Yeah, differential equations.
Differential equation. Great. So, any one book you would recommend that every student should read once in their life?
Yeah, that's a difficult question. There are so many books.
Yeah.
I would say, all the students, I don't know whether you are familiar with Tirukkural.
Oh.
That's, it consists of 1330 just 7-word poems.
Okay.
So it tells all about your life, everything about your life. So that's called Tirukkural. Tiru means, Kural means shortened versions. Okay.
Wonderful.
I think there are English translations also. So I think everybody should learn this Tirukkural to get to the basis of human life. Yes.
I will definitely look
Yeah.
on that book. So, what is the simplest example of non-linear behavior in nature? One of the simplest.
Yeah. And your neuronal system, neuron, the simplest or the basic nonlinear dynamical system.
Yeah. So there.
Or even a pendulum.
Yeah.
The pendulum itself is essentially a nonlinear system, but only under small oscillations, it's a linear dynamical system.
Yes. Sir, I would like to give you a situation and you would have to choose among this. So, would you rather be stuck in a time loop with a Schrodinger's cat or be trapped in a room with a non-linear equation which never converges, like which never gets solved? Which one would you choose among these two?
Yeah, I will use the nonlinear equation.
Non-linear. Sir, last but not the least. So, do you believe in aliens?
I'm sure they should be.
They should be there. So, if hypothetically speaking, if ever aliens landed on Earth and they asked you for being a volunteer for them, like working with them on some experiment or something, would you be willing to volunteer with them?
I think so.
Yeah, great choice, sir. Thank you so much, sir. That's
Okay.
it for the
It's a
rapid fire
pleasure
round.
talking to all these young people. So I wish you all the best.
Thank you so much, sir.
Like, share,
And
and subscribe to Adaptiv.
Thank you so much, sir. It was wonderful.